Hello all and welcome back. So in this video, let's continue our discussion and now find space complexity for some algorithm which we have studied. So let's get started. Now, when we have to find the space complexity, we have already discussed on the basics, right? What exactly do we consider in space complexity and majorly what all we can control and what we cannot. For example, input space, the input which you are getting is something which we don't have any control over. But auxiliary space is something which we can actually control as well as I would say optimize on, right? As well as if let's say some algorithm is there where we are, let's say, creating lots of those arrays. Okay, now if you will remember when we were doing recursion, right? There was a reason when I was saying that let us use the indexes like I and j start and these pointers instead of slicing our list, right? The reason for that was actually that when you slice your list, it creates a copy. So in a way, some space is getting used for that particular copy in your algorithm. Okay. So we're gonna look at that in recursive part, but for the time being, let us now focus and first see for the insertion sort. We already discussed on the bubble sort in the last video, so let's see the code for insertion sort as well, everyone. So this is the code of insertion sort which is front of us. Now here, if I see, then we have just created some key, some j. Then I'm running some loop and doing some operations. Again, j is created here, but that is basically updated from the scope, right? And finally, I'm just updating. Okay, so I don't see I've created any new memory here apart from these small variables key and j. I don't think any major memory we have created which is dependent on the length of my array, right? So doesn't matter if I give it a 3 element array or 3 billion element array, it's just going to create these elements and going to work on that, right? On that note, I believe that it should have a constant space. So O n of 0. It is not dependent on it, which is equals to O1, right? On the same understanding, if let's say now I have some loop, okay, let's say I'm given some array only, array, and I need to find the maximum, and I need to find find the maximum of this array. So I'm going to do something like this for I in array. If my array of I is greater than answer, then I can just say answer is equals to array of I, right? Again, if it's in a function, we can return, else we can print, so that should not be a problem. If you will see here again, we are not creating any new memory which is dependent on the size of my array, right? I'm just actually creating an answer variable which is very small, which is constant as well. So here as well, we will be creating only O of n0 space, right? I hope that is pretty easy to understand, right? Like we are not creating any extra memory. And I have already told you these small variables, they don't have a part to play as such, right? So the understanding is that all these algorithms, they are constant space algorithms. Your bubble sort, insertion sort, selection sort, all these are your constant space algorithm. For algorithms where we have written code iteratively, it is pretty easy to find. Just see that if you are actually creating copies or creating something based on your input which you are getting. If you are creating some extra space, not these small variables, if you're creating some extra space, then that is where actually you should say that, yeah, you are using some memory. It is not constant. Okay, cool. So if that is clear, let us actually move to the major part, which is space complexity of our recursive algorithm. Now coming to recursive algorithm, let us write the code for, let's say, factorial of a number, right? Some algorithm which we have studied. So coming to space complexity of recursive algorithm. For factorial, let's say for finding out factorial of n, I'm just going to write the code something like this, right? So def factorial of n, if my n is less than equals to 1, then I can just return 1. Else I just return factorial of n minus 1, right? So something like this actually I intend to do. Now here, if you will see, we have not even created a single variable, let alone any array or list, which is created on the basis of my factorial. So should the complexity here be O of 1? Well, if you are thinking like that, then again, we have to revisit the way we did our time complexity analysis of recursive algorithm. in recursion, we have to make sure that we can also count exactly what is happening when we go inside this, when this call is made. Yes, we are not creating any particular variable, any particular array in the working, but this return factorial, right? This actually will be invoking another function call, and this function call will be waiting in the memory till then. If you remember, then I showed you, and I'm again going to show you this in Python tutor as well, so that you're able to actually visualize pretty nicely that these functions, they remain in the memory and they are dependent on your n. So for example, if let's say I'm calling for factorial of 10, then I will have some functions which are going to wait, and that will be dependent on n, right? So if n will be 10, then I will have 10 functions waiting, right? As compared to, let's say, if the function call were some constant, then I would have said that, okay, it is anyway O and 0. But here, let us see how we are going to find the same. Okay, so exactly what I'm saying, and let me show you that as well. We are going to make a function call for n, right? And this function, let's say, takes up some k space, right? Now, because this function is calling other functions beneath it, which is going to be n minus 1, then let's say n minus 2, dot 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 all the way till 1, where it's going to return. I think spaces from this should be considered, and let me show and help you visualize this as well. So let us go to Python tutor, def factorial n. If n is less than or equal to 1, then we can just return 1, and else we can return n into factorial of n minus 1, right? I think I didn't write this here, so 1 second. Great. So we are not creating any new variable as such. We are just using what we are given, and let me just use factorial of 5, maybe, yeah, and I can just print, so we see the answer, but it should be fine. Cool. So let us now try to execute it. We have seen this many times. Like we will have all these methods, right, which we will be waiting. So let me just zoom it a little bit. Yeah, great. So first, this factorial is created in global frame. Next, if we move forward, factorial with n is equals to 5 is created. Moving forward again, factorial with 4 is created. But one thing which you will actually notice here is that this 5 is still in the memory. It is taking up some space, right? And your function, these number of functions, that is dependent on n. That is not some constant. Okay. So let us move forward. 3, 2, and finally 1. Okay. So at this particular point, I have 5 functions. If n would have been 10, then I would surely have 10 functions waiting in my memory. So the point which I want to explain you is that the number of functions waiting in your memory, it is not some constant. It is dependent on your input n. It is very, very well dependent on your input n. Okay. So for example, this n, if it is 100, then I will at some point have 100 functions waiting. If it is 1000, then 1000 functions waiting. It is changing with respect to my n. And thus, let's say if I'm saying that, hey, each function takes up some k memory, then I can say very comfortably that kn is going to be my space complexity. The reason is that I have n functions waiting to get my answer. And you will see that once this s function, like let's say these are the n functions, that would be the maximum in the memory. Okay. So one thing more which we have studied, if I see what the graph, it's going to be something like this. It's going to increase, gonna reach out to the maximum. Okay, when your n is equals to 1, and then decrease. So I have already told you that how we take the peak memory. Now I'm not going to add all these memories. Okay, they are intermediate memories. So at the peak level, we will have n functions waiting when n is equals to 1. And thus I can say very comfortably that n into k is going to be my space complexity. So let us write the same down in our notes as well. Okay, I hope this is clear by seeing this visually. Again, everything is going to get returned and I'm going to get my answer. Okay. Great. So what I'm saying is, what I want to actually say is that recursion, let me write it in some box. Yeah, 1 second. Yeah. Recursion is not free. And this is the reason while I was teaching you recursion, I told you about the recursion limit, about the stack memory, all these things, right? So we have this limit so that the overall stack memory, that doesn't get overflow, right? That's where Stack Overflow comes into picture as well, the popular website. So yeah, so recursion is never free. Okay, the functions waiting for answers takes up some space, and because the number of function calls is dependent on my n, it is not constant, hence I will always say that I'm going to take that much space. So this is going to be my time complexity, right? So let me just draw this as well, everyone, so that you remember. Please make sure that you download these notes. These will be provided to you and will be very helpful in remembering or revising when you want to give any interview or anything, right? That's why I'm making sure that I'm writing each and everything. So at peak, we will have n is equals to 1 and n functions waiting, right? So we will have n functions waiting here and n is going to be 1. So again, recursion is not free. Some extra space is required. Now we have already seen for iterative based algorithm, which you should be very easy to calculate. Let me show you one more algorithm in this video only. So that is going to be binary search. Okay. The way we do binary search by recursion, binary search by recursion. Now here again, we have done this analysis a lot of time. We will be given an array. Okay. At each point, I'm going to divide my problem. Second, I'm going to divide my problem into half. N by 2. Let me make it half. 1 second. N by 4, something like this, right? So again, the understanding is the same. If each of these functions, let's say they are taking up k space in my memory, k, then if I'm able to count the function calls, okay, and again, one thing more, remember, like I have to count the total function call which will be maximum at a point, right? The peak. So if I can count all these things, okay, then I can say my answer is going to be something like this: k into number of functions. If that's the case, then we have done this a lot of time, that how much are these functions going to be. If you have not seen the previous video, please go and see that. We have done this calculation a lot of time. It's going to be n into, sorry, my bad, k into log 2 to the power n. Again, the basic understanding is same only. We are calculating it for the worst case, right? If you find it in the very first place, then again, these function calls are not going to get made, right? So always remember, we are calculating the O, big O, which is the worst case, something which you have studied. So the same features, the same overall concept get extended to the space complexity as well. And in worst case, we will have log n functions waiting, right? Now, many of you might be thinking that recursively binary search will have some complexity. Yes, absolutely. The same is not true if we do it iteratively. And this is the reason many times in very optimized environment, right? Let's say if you give some OAs or do some questions on, let's say, lead code or some other website, many times it can happen that your recursive solution might not get accepted because let's say the input is very large, right? But your overall solution for this iterative will gonna get accepted. Okay, and that's the reason for that particular thing, that space is also considered, right? So it is not that recursion is free. So many times you will see that you will get some error if you try to just submit the recursive solution, but on iteration the same solution is gonna get accepted. The reason is they are going to be space complexity, not the time complexity. Okay, because time complexity for both of them are same. Now it is the space complexity which is giving you the problem. Okay, so I hope that is clear, everyone. We are going to see that at a lot of places, and that will actually one of the reason we study about DP as well, right? So when I'm gonna teach you DP in the module, then you will also understand why DP is required and how it is helpful in space and time complexity both. Okay, but yes, don't feel like if your solution is not getting accepted for recursion, so recursion is not useful. No, I think till now we have seen that how recursion help us to even think the thought process overall, right? How to write easily the code, and then we can of course easily even transform the same into iterative solution or something, right? So it's not that recursion is bad, It's just that it has some space complexity caveat behind it because functions are waiting in the memory, right? Cool, everyone. So I hope this is also clear, the overall understanding. And again, not just giving you it directly, making sure that you understand the whole process. That is something which I want all of you to pay focus on. Process is the most important thing because if you understand the process, it's going to stay with you, and you can find every answer for even some algorithm which you have never written, or let's say which you are trying to write. So remembering will not help you to understand these things. Understanding the process will, and that is something which you can even use to explain your interview tomorrow. So please make sure that you always and always focus on the process the way I'm teaching, and you will be able to crack any of your product-based companies or any company interview for that matter. Okay, cool then everyone. Thanks a lot. So let's meet in the next video. Thank you.